the camera rolling.
Yeah, I should time it.
Okay, Chris, let's hear the story.
Give me the same thing you got me. Alright, well, when I was trying to decide what my demonstration presentation would be, I figured I should do something that's in my career path. So being the aspiring structural engineer that I am, I thought it'd be a good idea to do a simple truss analysis. So to get started here, I'd just like to say some reasons that you see trusses throughout the world, whether it's bridges or roofs. They carry strictly axial loads. And to demonstrate what an axial load is, it's just simply tension, pulling, or compression being compressed. And you don't have to worry about torsion, which is actually twisting or bending, which makes it easier to analyze, and it lets you use all different sorts of materials for when you're designing your truss. And then the geometry of them makes them strong. Basically, you'll very seldom ever see a truss that isn't built out of mostly triangles, which triangles are an extremely strong, simple shape that can be constructed very easily. And then they can be built off-site, which is a huge deal for construction costs. You can bring in, you can have them all uniform, come in with a crane, drop them onto your column supports, and actually design your roof. So here we'll show a couple examples of trusses in the real world. This is the Oakland Bay Bridge, sorry. And as you can see, it's a pretty sophisticated truss system here. We're not going to get any of the details like this, but you can see throughout it's all triangles. And even on the column supports, when it's bringing the loading down to the surface here, it's more trusses inside here. And the reason is because they're efficient, they're strong, and you know it's going to be a sturdy structure. So then just a simple roof truss. This is more something you see on an everyday basis in construction. And as you can tell, these are all uniform, every single one of these trusses throughout. And basically what you have is, a consultant come in, they build all of these to whatever specs you wanted it. You come in with a crane and you lower them, depending on your dimensions, right on your column supports. And it's a pretty simple way to do construction, and it's very cost efficient. So next, we'll actually get into the analysis of a truss. There's basically two ways that you can approach a truss like this. You can do the method of joints, which would be today's demonstration, where you isolate a joint and then you apply Newton's second law, which is force equal to mass times acceleration. And the absolute beauty of civil engineering is that mass times acceleration equals 0. If your structure's moving, you have problems, and you need to go back to the drawing board. And then the method of sections, it's a bit more difficult, takes a little more analytical practice to get used to it, and we won't get into that today due to time constraints. So basically, we need a truss to analyze. Here we go, we have a truss to analyze. So as you can see here, you can't just put a truss out in the middle of nowhere, you need to have supports to actually support it down to the ground. And right here you can see this is a roller support, which I have a picture of here. And roller supports, they only give you a force in one direction. This is on your technical terms, your handout too, if you want a little better definition. They'll only give you, in this case, a force in the vertical component here. So the first step for analyzing the truss is we come in and we draw our forces. So if we label each point, or each joint here, A, B, and C, we'll have a force from the roller support here called Cy. And then next, if you have a force in the X acting here, if you don't have something else going against that force, it's going to roll. So we implement a pin support here. And as you can see, a pin support will be able to take force components from both the horizontal and vertical direction. So we come back to our drawing board here, and we have AY and AX. And like I said here, we're going to basically take one joint, and I'm going to start here with B, and we're going to isolate it and evaluate it using Newton's second law. And just to explain my, this is 100 kips, which one kip is equal to 1,000 pounds. So you're actually applying 100,000 pounds to this truss here, which may seem like that's a ton of weight, but in the real world that's really not that rare to see. So using Newton's second law, we can use the sum of the forces in the X equal to 0, and the sum of the forces in the Y is equal to 0. And basically the number one rule of this, always determine what your coordinate system is. So you have your X, and we're calling X to the right is positive, and Y up is positive, so Y down be negative. So then we come in, we'll label our forces and our members. So we have member force AB and force BC. And we'll start by just doing forces in the X. So we have 100 kips, just acting to the right, so it's positive. And then we subtract. But as you can see here, this force AB is actually working in two different components. So it's working both in the Y and the X. So this needs to be broken up into components because all we want is this part of that force. So we come into this, and this can be done either two ways, using the geometry of the truss, or you can actually use this specific angle. For here, I'm just going to do the geometry of the truss, and I made this simpler just for time constraints here. So basically, you have your x component here, and your hypotenuse, and that's how you're going to break it in to make sure it's only a force in the x. So you come over and you have your x component, which is 4 feet, divided by 5 feet, your hypotenuse, and that'll all be equal to 0, because you have no more forces working in your x. So that's just simple algebra, and you end up getting that FAB is equal to 125 kips. I mean, that kind of makes sense too. You can stand back and you can look at this. Okay, so if I have a force that's coming in 100 kips that way, and this isn't actually exactly on the same plane as it, it's going to need more force to make up for that. So then we do our sum of our forces in the y, and FBC is going down, so it's negative. And then we have FAB, and that has a negative y component as well, so that's going to be negative FAB. We break it into components again. We'll have our y component over our hypotenuse, which would be 3 feet over 5 feet is equal to 0. We already know what FAB is, so it's pretty simple to solve for FBC. And you'll end up getting that FBC is equal to negative 75 kips. And now you might be thinking, I know when I first did this, why would you have a positive and a negative force? Basically, what happens is that since this is positive, we drew our arrow wrong. So this member actually is in tension, but this member, we drew this arrow wrong because we got a negative force, so it's actually working in compression, which means that it would actually shorten rather than elongate like a member would in tension. So I always come back through here and I label each, just to keep things forward. And then since we only are looking for the forces in the members right now, we'll come and we'll evaluate joint C. And after doing these for a while, you can start to realize when you're going to have zero force members, and this is actually going to be a zero force member. We'll just make sure that we can tell just off of applying Newton's second law here. So we'll have the 75 kip force coming down from FBC, because this is actually in the same plane here. And then we'll have our CY, and then FAC. So since we're only worried about the members that are occurring in the forces right now, because we're expecting our supports to be fine, we'll do the sum of the forces in the x is equal to 0. And basically all there is in the x is negative FAC is equal to 0. Negative 0 is still 0, so FAC is actually a zero force member. So now, in most problems, you're going to have kind of a problem statement for this. So we want to determine the area for a factor of safety of 2. And I don't have time to derive the equations, but basically you can relate stress, force is going to be equal to stress times area. And we were given in the problem statement that the ultimate strength of steel is 65 KSI, and KSI is kips per inches squared. So basically what you can do is you can come in here and be like, okay, this is going to be the ultimate strength that it needs before this member fails, or the ultimate stress that it needs for this member to fail. I also put a definition of this in your technical terms here. And what you're going to do is you're going to come over and be like, okay, what am I solving for? I need an area of a factor of safety of 2, and I know the ultimate strength. So I can make a, just again, simple algebra, force is equal to, or area is equal to force over stress, and then I can sub in the ultimate stress. And we're only going to figure out our area based on the member that's carrying the most amount of load here, which would be our member FAB. I mean, you can do it for this one too, but you're actually going to get a smaller area, and if you design them all on that, based on that area, this member would fail. So you come in here and you end up getting 1.923, I believe. Yeah, you end up getting 1.923 inches squared. Now, when you do this, this is just saying that that's the amount of area that you need to get it to fracture, so you don't want it based on that, or else your truss system will fail. So this is when you implement your factor of safety of 2, which is also in the problem statement. And you just say, okay, if I want a factor of safety of 2, I multiply the area times 2, and I end up getting 3.846 inches squared. And then you design your truss based on that dimension. So then, if you really wanted to, you could, again, I don't have time to derive equations again, so you're just going to take my word for it here. That deflection is equal to force times length over area times Young's modulus. Young's modulus is a material property, and you already solve for length, area, and force, so you can end up subbing all this in. You're going to get the deflection of that beam, AB, is 0.0627 inches. And this is basically how you do a simple truss analysis, and I guess that's all I had today, so if there's any questions, I'd be willing to answer them.
No questions? Okay, thank you very much.